just in theory.
Okay, thank you. So let me just sort of begin with the place that I left off last time. So we were, so this is what I will talk about today, about the Still-Simons formulation of gravity in ADS3, and that will lead to the similar formulation of the Vasiliev theory of higher spin fields on ADS3 as well. So the Still-Simons formulation comes via the by looking at the frame formulation of general relativity, which, as I said yesterday, has as its basic variables the frame field or the field bind and the spin connection. And in 3 dimensions, this can be traded for a single index field using the epsilon tensor. So using epsilon ABC, you can trade this for a single index field, the usual equations for so the usual equations that you have in the presence of a cosmological constant are for E and A. So this may not be familiar to many of you, but one is the torsion condition plus so the torsion condition reads like this, where I have defined EA to be the one form that you construct from this. Sorry, this is omega. B and omega is B is similar. These are both one forms. So this is a 2 form, and this is also a 2 form with the usual wedge product. So this torsion condition, this is the torsion is defined this way, and its vanishing is one equation. This is the analog of the equation that determines the Christoffel connection in terms of the metric. Here you can use this equation to determine these equations to determine the omega in terms of the field binds. So that's the condition that tells you the relation between the omega and E, and RA, which is the curvature, is defined in this way. So the curvature is d omega plus omega wedge omega, essentially, and the equation of motion in the presence of a cosmological constant is just given by this. So it's basically, this is like a density. So it's minus 1 over 2L square, so this is the cosmological constant. So this is the frame version of the Einstein equations, R mu nu equal to lambda times G mu nu. So these are the 2 equations in the frame language, and these follow from the action, which you can. So the way the action is conventionally written. So these follow from the Einstein-Hilbert action, which is written as 1 over 16 by G Newton integral. And in this frame language, it's written as trace of So this traces over the SO2, 1 or the SL2R, the gauge group indices, this A. In fact, we will often use the notation E, which is equal to EA JA, or omega, which is equal to omega A JA, where these are the generators of SO2, 1, and the tangent space indices. So you can think of these as 2x2 matrices. So let me maybe say that. So these are these are the adjoint representations. So these are 2x2 matrices, and if you want to be explicit, in fact, what we will often use is a combination of so this J0 equal to half of L1 plus L minus 1. So we'll use actually combinations which one calls L1, L0, and J2 is L0, where L0 is the Pauli matrix sigma 3, L1 is the Pauli matrix sigma, so sigma 3 is 0, 0. So just to be very explicit, sigma plus, which is this, and L minus 1 is minus sigma 3. So this is a convenient basis for these. So these are the natural SL2R generators, which obey Ln Ln equal to n minus n. So this is, so you can take these generators, construct these J0, J1, J2, or maybe I should have called it J1, J2, J3. In any case, these are the generators of SO2, 1, which, as I said, is the same as SL2R. So this is what we have over here. So you take a trace of these matrices, E wedge R. So R is just RAJA, and similarly you have over here. So this is like the R plus lambda term that you normally have in the usual Einstein-Hilbert action. This is just a frame formulation of all this. Okay, so this was maybe, so this is still conventional, I mean, this is still standard. It is just written in the frame formulation. But as I mentioned yesterday, it's convenient to introduce these combinations. Which are sums and differences of these connections. So you introduce corresponding one forms A and A tilde. The nice thing is that, as I mentioned, these transform as SL2R gauge fields under the local Lorentz. Under the local Lorentz transformations. these transform as gauge fields in the conventional way that non-abelian gauge fields transform. The nice thing is that in terms of these, those two equations take a very nice simple form. So in terms of A and A tilde A, the equations of motion, so namely these two, let me call them so these 1 and 2 take the form so this is just a matter of algebra. You can verify that and so it's a good exercise. So this are now two sets of decoupled equations for A and A tilde. So if you take sort of sum and difference of 1 and 2, you can see that they can be written in this form. So it's a neat way of writing those two equations. And if you have, if you're familiar a little bit with non-abelian gauge theories, you immediately recognize that this is nothing but the field strength associated with the SL2R gauge field. So if you have some SL2R gauge field in A tilde, then you would define the non-abelian field strength as dA plus A wedge A with the structure constants of the group, which in this case the SO2, 1 group, which is the epsilon ABC. And so this is the field strength and denoting it by F. So the statement is that the equations of motion in terms of the non-abelian gauge fields A and A tilde are very simple. They are just the gauge field equal to field strength equal to 0, F of A tilde equal to 0. So you get two decoupled equations starting from those two sets of equations up there. So this is the very nice simplification of this gauge language. So by the way, this FA is can be written as FA is the same as the usual FA mu nu dx. So it's a two form, and that's what this is. So it's the usual non-abelian field strength. So these equations of motion are very simple. They are saying that these connections A have vanishing field strength, and this sort of equations follow from an action which maybe you may have seen before. They are what is called, they follow from the so-called Chern-Simons action. So the Chern-Simons action is a very famous action in 3 dimensions that you can write down. It's a topological action for a gauge field. It's different from the Yang-Mills action, which gives the Yang-Mills action, when you vary with respect to the gauge field, gives the Yang-Mills equation of motion, which tells you about sort of the d of f, the covariant derivative of f contracted d of star f really equal to 0. But these are not the Yang-Mills equations of motion. So the Einstein equations here are not the Yang-Mills equations. They are much simpler. They're just saying f equal to 0. And these equations follow from this kind of Chern-Simons action, which is conventionally normalized with a sort of a coupling constant outside, which I'll denote by k hat. So this is a very, maybe if you have not seen it before, it looks at first sight quite unusual. It looks as ADA plus 2/3 A cubed. So in fact, it does not even look gauge invariant, but one can show that it is modulo various boundary terms and so on. It is actually gauge invariant, and the equation of motion is it's a simple exercise to show that if you vary with respect to A, you get the equation of motion is precisely that F is equal to 0. Yeah.
D3x is not necessary.
Sorry?
In this definition for the Chern-Simons action, D3x, the volume element, D3x is not necessary.
I mean, I'm just saying that it's just the integral. I mean, it is, of course, it's independent of the metric, but no, what do you mean it is not necessary? It is just the volume integral. That's it.
A and the dA is a contraction of vector method.
Okay, yeah, so if I write in terms of the form language, that's true. I'm mixing notations, thank you. If I write in terms of the form language, then I don't need to write that here. So it's the integral over whatever three-dimensional space-time we are writing, yeah. That's true. So, any other questions about this? This is a very beautiful theory, which has a lot of deep connections into mathematics also. In fact, this was the work on the Chern-Simons theory was what led to the first physicist, Edward Witten, getting the first and only physicist who has gotten the Fields Medal in mathematics based on his realization that this topological field theory or SU2 and compact gauge groups leads to interesting topological invariance. But anyway, that's not what we are going to talk about. So these actions therefore follow from, so these equations of motion follow from this kind of action. So we can write an action, and we have, of course, not just A, but we also have A tilde. And so in fact, it's a good exercise to check that this Einstein-Hilbert action that I've written there can be written as just the difference of the Chern-Simons action for A and the Chern-Simons action for A tilde with this, and in fact, if you compare, so all you need to do is put in the definition of A and A tilde in terms of omega and E, and work out all these terms, and you will find that using this definition for R, that it becomes exactly this, and that allows you to fix this overall factor. This k hat over 4 pi is, so you find that k hat over 4, k hat is equal to L over 4 times G Newton by comparing with this overall factor that is there outside. Okay, so so this is so in fact you can understand. So you can see that the variation of this equation, this action will give you both these, because these are just two decoupled actions for A and A tilde. So varying with respect to A will give you this, and varying with respect to A tilde will give you f of A tilde equal to 0. And the relative minus sign is actually also fixed by parity. You can see that under parity transformation, A and A tilde get interchanged, so demanding the right. So you can actually, even without doing the computation that I just mentioned, even without showing that this is equal to this, you can show that the action must be of this form. And then, of course, comparing to this allows you to fix the overall constant, and there's the so-called level of the Chern-Simons theory in terms of the cosmological constant and G Newton. Okay, any questions? So it's a good exercise if you want to sort of get familiar with this, to try to work this out. So this is the Chern-Simons formulation, and this formulation is very useful it's very useful to recast many of the results of 3D gravity in this language. So for instance, you can look at the various solutions to the 3D gravity with a cosmological constant. There are many interesting non-trivial solutions, in particular the so-called BTZ black holes. So of course, global ADS3 is a solution of the Einstein equations with a cosmological constant, negative cosmological constant. But there are other non-trivial solutions which are black holes, the so-called BTZ black holes, which play, again, a very important role in understanding the entropy of many non-trivial black holes. So these have, so these are all solutions of 3D gravity with a cosmological constant. You can talk now. You can look at these solutions from the point of view of this frame language or this Chern-Simons language, and that's very that provides a very useful point of view. So so what are solutions? So the solutions of the equation of motion correspond to just finding so-called flat connections. Connections which have zero field strength are called flat connections. So you can so we need to find solutions to the equations of motion which are asymptotically ADS3 . So that's what you would do if you were a general relativist. You would try to find all solutions which are asymptotically ADS3 in the frame language. So these correspond to a class of flat connections. So it corresponds to a class of flat connections which obey particular boundary conditions. So you can they can be so they can be parametrized. A useful way to parameterize them is as follows. So we'll so ADS3, as I drew in my lecture yesterday, ADS3 has this sort of geometry of a solid cylinder, so what we will use as coordinates are a radial coordinate, which I'll call rho, an angular coordinate along the circle direction, which we'll call phi, and a time coordinate t. So, so in terms of rho, phi, and t, and sometimes the phi and t, it's useful to combine into sort of two coordinates, w and w bar, where w is equal to phi plus I t by L, and w bar is phi minus. So, so in terms of these coordinates, rho and rho w bar, or rho phi and t, which are as follows. One thing you can do. So you want to find these flat connections modulo gauge transformations. So you can use gauge transformations cleverly to pull out the radial dependence. So by the way, just to give you some intuition, for this f equal to 0 means basically that there is very few, there's no real propagating degree of freedom in the bulk, because the field strength is 0. So so all the freedom is in some sense topological. It is sort of so there's no bulk degree of freedom. It will turn out that there are sort of degrees of freedom on the boundary of this. So that's part of this holography. That's an explicit realization of this holography, that the degrees of freedom are on the boundary in this particular case. And so you can use the gauge transformation to actually get rid of the boundary dependence, and it's useful, it's convenient to parameterize it as follows. So you can actually write by a gauge transformation involving B, which if I define B to be e to the rho times L naught, so this is a matrix, remember L naught is that sigma 3 matrix, so this is an SL element of SL2R. So I make a gauge transformation essentially by B. I can parameterize the solutions in terms of this B, and then all the dynamics is in these two functions. So the solution to can show that the general solution to the equations of motion can be parameterized in this way, involving just a holomorphic function A of W and A bar of W bar, and these where this A of W or A of Z can be written as L1 plus